This second part related to defining your own function. We're going to see some functions applied to a specific problem in civil engineering. And I have the problem defined here, the flow in open channels. A quick presentation: if you have an open channel of rectangular cross-section of width B and depth Y, where there is a discharge of volume per unit time Q going downhill on a slope that will be how many vertical distance per unit horizontal distance. The slope is called S sub 0 at a depth Y, and then there's a coefficient called the Manning's coefficient, which is determined by the type of lining of the channel, and then all these variables are related by a formula that we use in open channel called the Manning's formula, that says that the discharge Q is equal to a certain coefficient of units. This changes if you use units of the English system or the international system, multiplied by the square root of the slope, which is a dimensionless number, divided by the Manning's coefficient, which is also dimensionless, multiplied by the area, B times Y raised to the 5/3, divided by something called the weather perimeter, which is the bottom width B times twice the Y, which is basically the perimeter of the channel in contact with the water, raised to the 2/3. This is an empirical equation. It's not even dimensionally correct, but it works. And so we have that for the international system, Cu is equal to 1, and we have a channel with a slope, relative small slope of 1.25 10 to the minus 4, and the Manning's coefficient of 0.012, typical for concrete. And we're going to treat the discharge Q as a function of the geometry of the channel, the bottom width, and the depth. And so we basically, on the left-hand side, declare QB, function of By, equal to this right-hand side, exactly as it is. We already taken Cu as 1, and suppose that we have B equal to 2 and Y equal 0.5. Then the discharge in cubic meters per second will be 0.4479. If the width is 2 meters and the depth 1 meter, there will be 1.739. A plot of the discharge for a bottom width of 2 as a function of the depth. We call it the depth Y, but in plotting here, we always have to use X as a requirement of SMath Studio. And so it shows that when the depth goes from 0 to 8 meters, the discharge is almost a linear function. If I vary the width of the channel and keep the depth constant at 2, then there's a slight curvature here, but then it's pretty much straight. Let's see what I did here. I think I went too much down. Close this. Okay. So here's the function. You can plot this function as a function of qxy, for which you will insert a three-dimensional plot and present here the function q of xy, and it gives you that. You can drag it around and see that it's not a very clear variation, but it shows it's a function of two variables. You can plot these charges for different bottom widths, for different depths in here, and the colors that will be produced will be in this order: blue, red, green, pink, orange. And so that will be a graphical representation of this function. Now, the reason why I'm presenting this function right here is because I want to use it with the solve function to solve for a particular problem. So redefining here the function, or just typing it again actually, using Cu equal 1, slope of 10 to the minus 4, the Manning's coefficient of 0.12. If I give you a discharge of 1.5 cubic meters per second and a bottom width of 2 meters, what will be the depth of flow? And so you can just type right here and say solve Q of By, space bar, control equal, that's the Boolean equal sign, Q dot 0, that's the value of Q0 that we define over here, space bar, comma, Y equals. So it solves for Y, sorry, in terms of the function, this one, equal to a certain value of Q0, which will be the discharge for this particular channel. Suppose that I change the Manning's coefficient into something rougher, like 0. Double that. And column 0.024. That's going to change my result right here. I didn't change it much. Anyway, the idea here is that I'm able to solve for this function, for this function given to a particular value for the different depths of flow Y. If I change B, that does have that doesn't make a difference. If I put B equal to again here, with the new value of n.12, I'm getting 1.801 meters. So something is not registering here. Let me check something. If I put n equal here, still running at 0.012. If I change this to 24, if I change to 0.5. The idea here that you can solve this equation. Now, let me try something else here. I'm going to do solve, and I'm going to put this control equal Q sub 0, comma, Y equals. I made some modifications because I wasn't getting the same result, or I was getting the same result even when I changed n equals 0.24. So what I did, I cleared all the variables involved in the definition of this QBY, and before I defined the function. And then I redefined my values of CU as 0, and then for this value of Q0 and B, I'm solving for Y, I'm getting the same result as I expected, and N is equal to 0.24. If I change this to 0.12, oops, sorry. I change it to 1.24, 2.04, and it changes the value there. So that now it's responding as it should be. You just have to be careful that you don't carry a value that is stuck into your function. And that's why it was important for me to clear all these variables before I define QBY. And now I am sure that I'm getting the same results. This is something I was using to check. But for example, here for Q sub 0, I'm going to eliminate this. I am just here just checking on those results. This could be eliminated too. And that's what I wanted to demonstrate, the use of those functions. And so, for example, suppose that we want to find the channel width that is necessary if you have a discharge of 1.8 cubic meters per second and Y equal 1.2, then you find this result solving for B. And so I wanted to demonstrate the use of solve for the case of functions that you define, and in this case I was defining this function for an open channel. This could be applied to any discipline of physics or engineering, and so I just wanted to do that